This is the third lecture, which is dedicated to the first practical application of all the equations we previously discovered during the previous lecture. And so for today you will see for what purpose we have this kind of relation, and specifically for the designs of nozzles and thrusters. So the starting point is always the same. We suppose we have only one directional flow, and this one directional flow can be through, for today, it's specifically such kind of structure, which is called the nozzle. Okay, and in this nozzle, we suppose we are only interested into the mean flow. Okay, it means at some specific location, it's completely possible, for example, here to have such kind of velocity fields, but it's not what we are interested in. We are only interested into the mean, the average motion, and so we suppose all along the flow, all which is interesting for us is that. Okay, so it's one-dimensional, it's only stationary, ideal gas, isentropic, and so on, all the hypotheses we already saw during the previous lecture. And we know that from that, it's possible to combine all of this and to obtain this kind of ugly but really simple rules or really simple equations that are combining only pressure, temperature, and density at two different locations. And this equation are combining at two different locations and only with the related Mach number on only one property for the gas, which is the gamma. So the heat capacity ratio. Okay, so it's really simple, and it can be, for example, computed in any kind of spreadsheet software without any trouble. It's really not complicated. Okay. So from that, basic definition, what is a nozzle? A nozzle is by definition a converging and diverging fluid, tube, with the minimum area, the minimum section, cross-section, which is called the throat. Okay, and so you have the converging part, so all of the flow is obviously in this direction, and we will suppose that, for example, the initial speed at the entrance of this nozzle is called V. Okay, so with the usual bar that means average. And this one is the converging part, and once you pass through the throat, you have the diverging part. So if we get back for a few minutes on the fluid mechanics, you already know. So the one which was based on incompressible flow. So we suppose we don't have any variation of density of the gas. We know just in applying this conservation of mass, so it's exactly the conservation of mass we defined during this lecture, but it's exactly the same as the one you previously saw during your previous lectures of fluid mechanics. Because we are not considering any variation of density, it means the only parameter that varies are the mean speed, the average speed, and the cross-sectional area. Yes, you're right. Thank you. A decrease. I was already thinking about the velocity. If the fluid is supposed to be incompressible, if the flow is supposed to be incompressible, so no significant variation of density, it means if you decrease the cross-sectional area, you will also increase the speed at the same time. Okay? And one other effect of that is the decrease of pressure at throat, and so it's called the venturi. Okay? It's clear for everyone. It's just we decrease the cross-sectional area, and so we increase the kinetic energy of the flow. Okay, if you just remember this relation. Applying the conservation of mass, but the incompressible one, okay, we suppose that if we decrease the cross-sectional area, we will also increase the speed, and so we increase the kinetic energy of the flow. And as a consequence, we decrease the pressure, because we suppose we have approximately a conservation of mechanical energy. In incompressible behavior, to this corresponds an increase of the speed, and to this a decrease of the speed. But for us, it will be different, because we are supposing our fluid are compressible, so with possible variation of density. Using the definition of the speed of sound. So if you remember last week, it was the variation of pressure over density. Okay? So using this definition, it's possible to express the relative variation of density related to the variation of pressure over density, introducing the speed of sound, or the square of the speed of sound. This equation, it's also called the momentum equation. So we already saw this in the previous lecture. Okay? And in combining all of this, it's possible to express this variation of density as a function of only the variation of the relative velocity, of the Mach number. And if I use this and I replace it in the expression of the conservation of mass, I obtain the first fundamental equation which explains how this kind of system works, which is called the Hugoniot equation. On the Hugoniot equation, it's really simple. If you imagine your flow is subsonic, okay? Subsonic means the Mach number is lower than 1, so all of this part is positive. And if all of this part is positive, we have exactly the same relation as the one with an incompressible flows. So the cross-sectional area and the mean velocity are varying in an opposite direction. Okay? In the converging part, my flow is accelerating. In the diverging part, my flow is decelerating. But if you imagine your flow is supersonic, in this case, the Mach number is higher than 1, and all of this is negative. And so the behavior is completely the opposite. Because now, if you imagine you will decrease the cross-sectional area, you will also decrease the speed. This one is not really interesting. The interesting part is when you are going into the diverging part, and in increasing the cross-sectional area, you also increase the speed. This one is really interesting, because it will be possible this way to increase in 2 different steps. So I will explain just after that how it works. I will have an increase of the speed in this part because I suppose my flow is subsonic. I will reach a Mach number which equal to 1, so it corresponds to a critical Mach number or a shocked flow. And once I am here in sonic condition, here it's a supersonic. And so it's twice. I increase the speed once and in the second step. And at the end, it's exactly the way we can use to produce some flow at order of magnitude of kilometer per second as an exit velocity. Yes? Because I didn't finish. This one is the past, the one we already know, or it corresponds at the same time to a Mach number which is lower than 1, combining with the Hugoniot equation. But if I suppose now that my Mach number is larger than 1, so my flow is supersonic, and so I can suppose my flow is really compressible in this case. The compressibility of the flow is something which is not so sharp. It's more complicated. As you remember, it corresponds to the transonic flow, and the supersonic flow, and the hypersonic flow, and all of this range of Mach number are not really well separated. It's something which is progressive. But anyway, in this case, we suppose that for the global behavior of the flow, if the flow is subsonic, its behavior is exactly the same as an incompressible flow, at least on the way the parameters are varying. Not exactly the magnitude of this variation, but at least the sense of this variation. But if the flow is supersonic, the behavior is completely the opposite. And it's why we can emphasize on, okay, this one is really compressible, because this behavior is completely different from the previous one we already know. And so, in this case, if I suppose I have the decrease of cross-sectional area will also correspond to a decrease of the mean velocity here, on this also in the other sense. On what is a thruster? A thruster is a device that combines these 2 effects at the same time. You start with the subsonic part in the converging part, and so you are here. And once you reach the critical Mach number at float, after that you are in supersonic, and so a thruster is this. You have twice this effect. You increase the speed because you decrease the cross-sectional area in the converging part. You need to reach the Mach number equal to 1 at float, and after that, the rest of the flow is supersonic, and so you are increasing again the speed. Don't forget, at this part of the float, usually the velocity is really small. At the very beginning, it's called stagnation state. It's what happens inside the combustion chamber of the engine. You can just suppose that your flow is at rest. And so there is no Mach number, there is no velocity. And for some of this system, it's possible in 1 or 2 meters to go from rest, so 0, to couples of kilometers per second. And the only way to do so is using this effect. And so, the 3 main behavior on the 3 main parts of my nozzle, if I suppose I can work this way. In the subsonic zone, the flow has exactly the same behavior as it would be, for example, incompressible. In the supersonic zone, it's in the other sense, so the mean velocity and the cross-sectional area are actually evolving in the same way. And what is also important is if you want to go from a subsonic to a supersonic behavior, so in order to have a nozzle that works properly, it's called shocked, the only location when you can have the critical Mach number, so to reach the speed of sound, is at throat. Okay? This is the only way where it's possible to have the Mach number, and it's another consequence of the Hugonot equation. If you want to just consider that the Mach number is equal to 1, so it corresponds to, okay, I reach the speed of sound, it's a critical situation. The only possibility is where there is no relative variation of the cross-sectional area. So it corresponds exactly at this point. And so from that, how to practically produce thrust? Imagine you have an initial speed. I want to have a subsonic zone in the converging part of the nozzle in order to stay exactly on the same kind of behavior I already know from incompressible flows. And so if I decrease the cross-sectional area, I will increase the velocity, but I need to maintain sufficiently high pressure and temperature at the entrance, at the stagnation point, which is here, in order to reach the critical state here, so the Mach number, which is equal to 1. And once I reach this state, my system is shocked. And so now it's okay. It means I will have a supersonic flow at this point. There is no other possibility. And so I completely inverse the behavior. The global behavior is completely opposite. It means if I increase the cross-sectional area, I will also increase the velocity. And so I increase the velocity once again in order to produce thrust. Remember, the thrust is always proportional to the exit velocity. Okay? So the larger the exit velocity, the larger the thrust. And it's exactly the way this kind of engines are actually working. It's also possible to use this kind of device at the outlet of an aircraft engine, but it's only for really specific purpose, mostly for military aircraft. Okay, for civil aircraft, it's not efficient from a propulsion efficiency point of view, and it's why we are not using this kind of device. It's only for military aircraft. And so now it will be possible to define some different location, and we will use this location in the rest. So all the parameters that are related to throat are noted with a superscript, with a star superscript. The one that corresponds to the stagnation state, so practically inside the combustion chamber, so where you don't have any velocity, the fluid is almost at rest, is noted with the subscript 0. Okay, so this one is the stagnation state. If your system is working in the nominal behavior, so we suppose you can reach the Mach number equal to the critical Mach number at throat. This one is called critical state. Here on the outlet cross-sectional area, it's noted with an E, a subscript E. This one is, we already used this notation, so it's just the outlet or exhaust. On all which is related to the ambience, to the surrounding air, is noted with a subscript infinite. So this one corresponds to the surrounding state. And so for all of these states, we will have a cross-sectional area exactly at this, but also a pressure, a density, and temperature, and so on. And because using our first relation, it was possible to establish a link between the same parameter but at two different locations, for example, the ratio of pressure, the ratio of density, and of temperature, it's completely possible to do so from one specific location to another one. And in this case, I suppose I can rely this parameter of pressure, but which is at throat, so that corresponds to the critical state, to any other kind of state. In this case, it's not 1, so we can imagine, for example, state 1 is here, for example, okay? So it corresponds to the cross-sectional area, which is note A1. And in this case, the ratio of pressure is just given by this kind of relation. On the same for density, on the same for temperature. And it will be possible just after that to rely, for example, to any location to the stagnation point, or to the stagnation to the critical, or to the critical to the outlet, and so on. And after that, we will have only really few and really simple relations just in order to check if our system is able to work or not. And also to calculate the outlet pressure and outlet velocity. The same from the stagnation point to any kind of location. So from the stagnation point, the one with the Mach number, which is equal to 0, so it's why half of this Mach number are actually disappearing, to any location. Okay? In this case, it's called 1, but it's just an example. This one is also interesting for external flows. So, for example, what happens just outside of the shape of an aircraft, and specifically of a spacecraft, because this one is really important, because this one is called stagnation temperature. So it's the temperature in the air which is really close to the wall. For example, you imagine you have any kind of shuttle. So you have, for example, this. Okay, this is the nose of the shuttle, and you have your fluid which is arriving this way. And if you are getting into a location which is really close to the wall, you will create a shock wave. So we already saw that last week, shock wave that looks like this. And after this shock wave, it's possible to find a location where the Mach number is really close to 0. Okay, it's called the ram effect. And so you are just decreasing the speed in order to reach some position which is really close to some rest position. But you were starting from a Mach number here that will really larger than 1. And for hypersonic flows, for example, the entry back into the atmosphere from space, it's possible to reach some Mach number which are really, really high. Because the density of the air at this altitude is really low, and so for a given velocity of your shuttle, if you are decreasing the speed of sound, you will also increase the Mach number. And so in increasing the Mach number, you will go from a specific temperature that maybe is really low to a really high temperature. Just imagine this Mach number is to the square, okay? So the ratio of temperature can be really, really high, and it's possible here to have some temperature that are of the order of magnitude on 10,000 kelvins. 10,000 kelvins. So almost everything would burn in such a situation, and it's the reason why we have some thermal shields which are made of ceramics. And if your Mach number is really close to 1, for example, you will have really moderate variation of temperature, but if you increase the Mach number, you can increase a lot the temperature at the stagnation point, and it's called the heat barrier. And it's exactly the reason it's really difficult for any kind of aircraft or spacecraft to fly at high value of Mach number. It's not really about pressure or about thrust or about drag. It's mostly about the heat barrier, because you will increase a lot the temperature of the skin of the system. So from that again, two specific locations. What happens from the stagnation point to the critical point? It is the simplest form of this relation. And this one is really interesting because it will give us the required pressure difference in order to reach the critical state. Okay? If you want your system to work, you need to reach Mach number equal to 1 at root. Okay? If, for example, you are only reaching, I don't know, 0.8 or 0.9, your system will not be shocked. And so you will have a decrease of the speed if you are increasing the cross-sectional area. So you are not producing thrust because you are just decreasing your speed. On thrust is speed, okay? The velocity. In order to obtain so, you will need to maintain a sufficiently high value of the pressure in the stagnation state, so in the combustion chamber, and this pressure is exactly P0. And so, if your ratio of pressure between the stagnation state and the throat is not at least equal to this value, you will not shock your flow. And so your system will not work. And it's exactly why at the very beginning of the starting process of a rocket engine, at the very beginning you have some fluid, some gas which is getting out, but you don't have this kind of effect. And it's once the combustion process is starting, or your turbopump is injecting the fluid inside the combustion chamber, now you will increase the pressure. And once this critical pressure in the stagnation state is reached, your system is really starting. And now we have the flame that are getting out of the rocket, and you will produce thrust. Okay? And for most of rocket engine, it just takes a few seconds to obtain this process. But not enough pressure, no thrust. Okay? And we will use this. And obviously, we have exactly the same relation for density, which is not so important. For temperature, it is, because temperature inside the stagnation state specifically is related to the temperature of the combustion, and we will do some calculation. It's called adiabatic flame temperature, just in order to have some order of magnitude. What happens, for example, when I mix some oxygen with some hydrogen, what is the level of temperature I can hope to reach inside the combustion chamber in order to just create this thrust effect, this nozzle effect. Clear enough? So how such a rocket is practically working? It looks like this. It is the simplest shape or the simplest structure we can imagine, but most of these engines are actually working exactly this way. So you have your stagnation point. The stagnation point corresponds to the inside of the combustion chamber, so it's the place you want to increase as much as possible pressure and temperature. The gas has only one possible behavior, is to getting out here. Okay, so there is no leak, there is no valve which is open, nothing. The only possibility for the gas to get out, so to decrease its own pressure, is to go this way. And so your gas will go here. And because at the beginning your Mach number is really lower than 1, because it's at rest, it's really close to 0, the behavior of the flow is subsonic. And so if I decrease the cross-sectional area, I will also increase the velocity. And if the pressure is high enough here, I will reach the Mach number here. Okay? And all what happens in the diverging part is only corresponding to supersonic behavior, supersonic. In this case, now, because I increase the cross-sectional area, I will also increase the speed until I reach this exhaust point where the velocity, the mean velocity of the gas is the highest. So if I take a look at the different parameters are already considered in this, 3 of them. The pressure, the temperature, and the Mach number. In the stagnation state, the Mach number is equal to 0. But the pressure and the temperature are really high due to combustion chamber, combustion process. And once I increase the Mach number, because the velocity is increasing, and I suppose I can reach the Mach number, which is equal to 1 at throat. At the same time, I will decrease the temperature, and I will decrease the pressure. And once I reach this kind of limit, after that, it's only about supersonic flow. And if you remember what I explained about compressible flows, it's impossible to transmit any mechanical information faster than the speed of sound. So it means because we reach the speed of sound here, this behavior is only due to this and absolutely independent of this one. This is one of the most interesting points about compressible flows. Once you reach the critical state, you absolutely don't mind about what happens after that. All the behavior of the flow, of the pressure, the mass flow rate, and everything is only related to this case. And you don't care about what happened here. And this is the reason why in some specific case, and I will show you some photos, some pictures, it's possible to have an outlet pressure which is lower than the ambient one. It's called an overexpanded nozzle. And it's really not good for the behavior, for the performance of the whole engine. But the pressure, the temperature, and the density you will obtain at point E is absolutely not related to what happens here. It's only related to this. Okay? So once you design properly your system and you make it work in a nominal condition, it doesn't matter that really happens here. It's only about what happens before. For only one reason, the influence of this part on this is only possible if the speed of the flow is lower than the speed of sound. Okay? Just remember, you are swimming in a river and you are swimming exactly at the same speed at the one of the river. You will stay at the same position. Okay? And if the speed of the river is higher than your own speed, you will just get back. Okay? Even if you are swimming. It's exactly the situation here. This is supersonic, so there is absolutely no possible physical way here for this air to have an influence of what happens here. This one is important because it's the only way we can express that the exhaust pressure can be different from the ambient one. Because if you are not considering this, you always have an equilibrium of pressure from this to this. If you just remember some probably exercise, you work on it with water or any kind of fluid in your previous lecture of fluid mechanics, you always consider that the outlet pressure was the ambient one. It's completely usual and it's fair because in this case you have a mechanical influence of the outlet to the inlet just because the flow of the fluid was really lower than the speed of sound. In this case it's not possible anymore. And so now it's possible to calculate the critical pressure or the relation between the stagnation and the critical point in order to obtain the shocked flow. It's also possible to reduce, to rely this to the exhaust pressure. Just using this relation, we can demonstrate really easily that it's completely possible to have an exit pressure, an exhaust pressure that is different from the ambient one. And this kind of situation only makes sense in compressible flows, and specifically in supersonic compressible flows. We want also to increase the Mach number at the exit, and we'll get back on this because it also increases the speed of sound and so the velocity for a given Mach number. Just imagine a simpler situation where you don't have any diverging part. You just have a converging part and that's it. So It could be, for example, a gas tank or any kind of system, and you open it, or you have some trouble on it, so it's just open. And you have a decrease of pressure, and this decrease of pressure is with an exit of the gas inside. This kind of flow on this kind of gas is just getting out on this. And there is only the converging part, okay? So the cross-sectional area is minimum here. What happens practically? I imagine I have my stagnation pressure and I have my surrounding pressure. At the very beginning, if there is an equilibrium of pressure, there is no constraint on the gas, and so no gas is getting out of the tank. Quite obvious. Now, if I increase this stagnation pressure, but in order to not reach the critical one at throat, I will just have a leak of gas outside. That's it. All the flow is just subsonic, and so I will always have an equilibrium of pressure here, okay? So if the stagnation pressure is lower than the critical one, then I have an equilibrium of pressure at the outlet of the system. So it's exactly how it works in usual fluid mechanics. Okay? And I increase again the pressure in order to reach the critical state at throat. So if I imagine now my P0 is exactly corresponding to the critical one. So it's not exactly that, it's just this, okay? So my P0 is equal to P critical. So now, if I increase my stagnation pressure in order to reach this value, by definition, my Mach number is equal to 1 here. And this is the last situation where you have an equilibrium of pressure. If I increase again, there is no equilibrium of pressure. It's impossible to have this because it means my Mach number is still equal to 1, but my pressure difference is decreasing. And in this case, the only physical way to equilibrate the pressure is to create shock waves. So in this case, I will have this kind of diamond structure, and all of these shock waves just corresponds to a really brutal variation of pressure in order to equilibrate. Because at the end, you will reach mechanical equilibrium. If you are just getting enough away from the outlet of the system, the pressure of the gas will be the same of the one of the surrounding. But in order to obtain so, because the pressure at the outlet is really high, higher than the ambient one, you will create a lot of shockwave structure, and it's the only way this gas can just equilibrate its pressure in order to reach the one of the ambient. And if I take a look at some practical example, I obtain exactly that. So this is examples of diamond shock waves which are at the outlet of some thrusters. So this one corresponds exactly to this kind of situation where the exit pressure is higher than the ambient one, and so the only possibility for the gas to equilibrate its pressure is to create this kind of diamond. So it's not exactly the diamond I draw because I have some gradient of chemical composition, but it's exactly this structure. In each of these locations, I have a different value of pressure until I reach equilibrium at the end. So it's a typical effect. When you just see this kind of picture, you can be absolutely sure that the outlet pressure here is really higher than the ambient one. And from propulsion efficiency, it's not the better solution. The best solution is really when the exhaust pressure is equal to the ambient one. It's called an ambient nozzle. In this case, the efficiency is really the best we can imagine. But because most of these engines are used to propel some rockets, and these rockets are changing their altitude, theoretically there is only one altitude when you reach this equilibrium. Before, the pressure is higher at the outlet, okay? And when you reach this point and you are going beyond this point, the pressure will be lower than this, and so you will be in an overexpand situation. The only way to maintain this would be to change the geometry of the nozzle in real time, but it's really complicated because this system are submitted to really high constraint of pressure and temperature, and to make this kind of geometry variable, it's complicated to design. And now if I extend this explanation to a complete nozzle, so to a converging-diverging system, it's a little bit more complicated because it's possible to reach different states of exit pressure, some pressure that are equal to the ambient one. It's called an ambient nozzle. Some of them that are higher than the ambient one, so it's an underexpanded, and some other, for example, at high altitude, where the exit pressure is lower than the ambient one. And so we suppose we have an overexpanded flow. And so if we suppose we are starting from the same condition here, we decrease the pressure in the converging part in order to increase the Mach number. We reach the critical pressure here, but depending exactly on what happens here, it's possible to have three different situations. An exit pressure which is higher than the ambient one, and so it's an underexpanded flow. An exit pressure which is exactly the ambient one, that corresponds to an ambient nozzle. And the last situation is an overexpanded, where your exit pressure is lower than the ambient one. And these three kind of behavior are corresponding to different performance of the rocket engine. So if I just start by the ideal situation where my nozzle is ambient. So the pressure is exactly the same at the outlet than in the ambience outside of the system. My flame will look like this. It's perfect situation. It corresponds to best performance. If I suppose my system is underexpanded, so the pressure is higher at the outlet than in the ambience, I will have an increase of the shape of the flame, okay, and you will have this kind of behavior. So it happens usually at really high altitude because there is no ambient pressure anymore. And so if you don't have any ambient pressure, your exit pressure is always higher than the ambient pressure. And so you have this kind of flow. So if you just look at some picture of rockets, but for example, the second stage of rockets at high altitude, usually the flames look like this. This one sometimes happen at low altitude when you have high values of ambient pressure. It's an overexpanded flow, and this one is really dangerous, okay? Because it's possible to have some vibration, some acoustic waves, and this one is the worst because it corresponds to physical mechanical constraint. Actually, the pressure wave are creating sort of vibration modes on the nozzle, and it's possible to completely destroy your engine with that. So it's why the pressure needs to be really enough in order to make the system work, okay? This situation happens depending on the altitude. So basically, this one is low altitude. This one just is supposed to happen at one altitude, the one where the pressure are equal. And this one is at high altitude. And this one corresponds to degraded behavior with lower propulsion efficiency, but it's not really possible to do in another way because it means you need to maintain and to change the geometry of the thruster. It exists, but it's only on prototypes, and it doesn't work on the long run. This one corresponds to, theoretically, the best situation, the best performance of the engine. Okay, so a quite famous example, Apollo 7. So it's quite old. This one is really nice because it's one of the best picture that has been taken of this Saturn V rocket at really high altitude, because usually you have clouds, you have a lot of turbulence in the air, and it's really complicated to take some picture of high altitude. In this case, I don't know exactly when it happens because we don't have the months, but probably this day the weather was absolutely perfect and it was possible to take this kind of picture, which is really impressive. And at such a high altitude, the atmospheric pressure is so low that you really see, it's clear here, the structure of the flame that corresponds to an underexpanded flow, okay? Because the exit pressure just at the outlet of the nozzle is really higher than the ambient one, because there is almost no ambient pressure anymore. You have exactly this kind of shape. From that, how to practically design such a nozzle, for us at least, it will only be related to the cross-sectional area. This is the only parameter we will manipulate, because all which is related to the exact shape of the nozzle, it's really too complicated. For us for the moment, maybe for you in the future, but for me clearly it's too complicated. What we want is to calculate the cross-sectional area in order to have a specific number, Mach number at the outlet. So this is just a simple graph with the Mach number in horizontal coordinate on the cross-sectional area, or the ratio of the cross-sectional area over the critical one in the vertical direction. Also, by definition, if your system is shocked, you know that at this location at throat, your Mach number is always equal to 1. It means it corresponds also to the minimum value of the cross-sectional area. This one corresponds to the diverging part, so the part where you are increasing at the same time the cross-sectional area on the speed. And if you are calculating, for example, you are just choosing the value of your cross-sectional area in order to obtain this value, for example, okay? So 2.6 to 2.7, the one of the throat, in such a condition, you will reach at the outlet 2.5 of Mach number. On all of our design exercise will just be based on this. I want to have a Mach number of 3 at the outlet because I want to produce such value of thrust, which is given. I need to calculate the outlet cross-sectional area in order to have more than 4 times the critical one. And so the Mach number of the outlet of the system is just related to the ratio, only of the ratio, not the value, the ratio of the cross-sectional areas. On the absolute value of cross-sectional area is related to the mass flow rate, because the thrust is the mass flow rate times the velocity. And so the velocity is given by the Mach number, but the other part of the momentum thrust is due to the mass flow rate. And in order to have the mass flow rate, we will calculate the cross-sectional area, its absolute value. And once we have the cross-sectional area ratio, we will calculate the outlet one. This is the only parameter we will manipulate, but it's really enough to understand how this kind of system works. And if you want to go on later on to just go into detail of this, there is a lot of interesting master's degrees or other which are dedicated to this. And so this famous mass flow rate, how to obtain this, it's not really complicated. You just have to consider it at throat, because we know that the mass flow rate is the same all along the system, all along the nozzle, from the stagnation point to the exit point, to the exhaust. And so if I consider this specifically at the critical state, it is just possible to detail, to change the expression, and at the end we have obtained something which is not really so complicated. One parameter which is noted here, alpha, that only depends on the gas. Okay, so it's this. So if you know the gas and you know the gamma, it's possible to calculate this. You have some example of values here depending on the gamma of the gas. The critical, the stagnation pressure, the stagnation temperature, the nature of the gas in the exhaust, in the nozzle, and the cross-sectional area. And so if you want to have it, if you have a specific requirement from the mass flow rate because you want to produce a specific thrust, and you know the value of the stagnation, temperature, and pressure, you just have to calculate the cross-sectional area in order to obtain this mass flow rate. And once you have this, and you want to reach a specific Mach number before, from the value of the critical of the cross-sectional area at throat, so the critical one, you just can get back on the one of the outlet depending on the Mach number you want. So the design process is really simple. It's only few relations we can combine. On how it is interesting to increase the Mach number at the outlet, because we want the velocity the highest as possible, okay? This velocity here is given by the product of the Mach number by the speed of sound, okay? And so this one is given only by the geometry, so basically on the ratio of the exit cross-sectional area over the critical one, but this one is related to temperature, okay? Remember just last week we saw this. So if we can increase the exit temperature, we will increase the speed of sound just at the outlet of the rocket. On increasing the speed of sound for a given Mach number, increase the velocity, the exit velocity. So we need to work on two different parameters. The parameters which are related to the Mach number, that are only combining the ratio of cross-sectional area, on a parameter which is related to the speed of sound, which is related to the exit temperature. And so in this case, again, the higher the better. It's why we want to maintain the highest temperature inside the stagnation state, inside the combustion chamber, in order to increase the whole temperature all along the nozzle, and so to increase the temperature, the speed of sound at the outlet. Clear enough? Yes? The last one is about few definition, but I don't know exactly if we will use it. It's more for your culture if you are looking into some books dedicated to rocket engine. You will get back sometimes on some effective velocity. For example, on Wikipedia, there's a lot of interesting data that are extracted from some existing rockets. And so if, for example, you want to include the pressure thrust, so the difference of pressure between the exit and the ambient, because now we know that in a rocket engine, we usually have this kind of difference. And in such a situation, in some situation, this difference is negative. An overexpanded, for example, overexpanded nozzle means that the exit pressure will be lower than the ambient one. And so you will decrease the thrust. It's why it's not good to be in such a situation. Okay? If you want to include all of this in just with only one velocity, it's possible to do so, and it's called effective velocity. Okay, so if you see some expression with the thrust which is combined with an effective velocity, don't panic, it's just another way to express the momentum thrust and the pressure thrust just in once using this kind of concept. It's not a physical velocity, it's just a parameter which is used to combine everything in just a simple relation. And so combined with the ISP, we obtain this. And also the characteristic velocity, this one is also used in order to design the system. It's only related to the mass flow rate, the initial pressure on the stagnation pressure on the critical, the throat cross-sectional area. And with that, it's possible, for example, to express the performance for a given couple of propellant. What does it mean? Sometimes it's interesting to compare. I want to make my system work with hydrogen on oxygen or with methane on oxygen. What will be the change of such a shift from one technology to another? The final thrust you will obtain is obviously depending on the geometry, on the type of the rocket, on a lot of parameters. But if you want to rely this only about the chemical composition of the fuel, of the propellant, it's possible to do so using this characteristic velocity, because the final temperature you will reach on both of these parameters are only depending on the nature of the gas, on the nature of the combustion chamber. So of the process combustion. So it means for a given couple of propellant, I will obtain only one reach. I will reach only one value of the combustion temperature that corresponds to the adiabatic flame temperature most of the time. This one is given by the nature of the flow, and so from that I can obtain a characteristic velocity. And it's why if you are looking in some technical documentation, you will have, it's really easy to find some tables with, okay, I have these couples of propellant, I have this characteristic velocity. Another couple of couplants means another characteristic velocity. And combining or comparing these values can just help you to decide which one is the most interesting for only, for example, the point of view of thrust. So I don't, probably we won't use this a lot. It's more about some technical culture if you want to go into the books related to this kind of topic. So just to remember this, absolutely nothing new. But now we have the physical process that explains how such kind of engine is supposed to work, or work usually. And I'm on time. It's miraculous, just 1 hour.